he's going to tell us about correlations enable lossless ergotropy transports.
Okay.
Let's listen to it.
Okay.
There's just some black slides that are in the middle, don't worry. Just keep them.
Oh, okay. All right. That's good to know. Okay, thank you very much. And also thanks to the organizers for this opportunity to be here at this lovely event. So, yeah, so I'm Karen, and I will basically talk about correlations that enable lossless ergotropy transport. So basically, this is going to go back to some ideas that were articulated in the first days of the conference. So, I mean, since this is the last talk of the session, I will not torture you with too many details. So I will basically try to communicate some general ideas behind our work. So this is already published in this journal. And well, so this is work done in the University of Potsdam in Germany in collaboration with Rick Simon and Janet Anders, who are also somewhere also in the University of Exeter. So this is kind of a joint thing. So yeah, the plan of the talk is basically I will start with a general introduction and talking about powering a device. So what does it mean to power a device with a quantum battery, right? So again, going back to the discussions during the first day, and then I will basically come to ergotropy transport, and you basically can see how this comes about, right, in this context. And then I will basically discuss the role of coherences, and I will start with 2 qubits, because 2 qubits are the simplest thing, right? And then I will describe like an ergotropy wire or something. Then I will go to larger systems, and then in time permitting, I will talk about concentration of ergotropy. And well, I will summarize. Right, so again, I mean, imagine like hopefully someday in the future, a generic scenario where we have like a quantum device, maybe designed better than this, but still. Right, and that is powered by a battery that is also supposedly a quantum system. Right, now this battery would have to do a number of things, right? So first of all, it would have to power the chip, right? It's a sort of the logical circuit that basically does all the interesting things in the machine, right? But then it would have to also sort of power some internal clocks that sort of control these operations, right? It would have to also operate classical input and output, because you will want something from the device, right? And it will have to sort of give you this information, right? So there are like a bunch of things that a typical quantum device, or I mean, pretty much any device, would do, right? It's not just one thing, right? And as we saw, like again, on Monday, right? So what happens is that when you tune your battery to do, for example, some kind of a calculation, you have to actually do a lot of fine-tuning, right? Some gaps, interactions, timing, and all of these things, right? And once you tune the battery for one thing, it becomes perhaps highly inefficient or completely inappropriate for another task, right? So basically, what we need is some kind of a general proxy for powering a device, right? So what would be kind of the general quantity that would that we can just think in blanket terms, right? So I transferred this amount of, in this case, as you see, ergotropy, right, to the device. Then the device can sort of already decide what it needs to use it for, right? So again, I mean, our point is that, you know, ergotropy would be like one of the key quantities to at least check against, right? I mean, we need to see how it works. So first of all, I mean, let me sort of remind you what ergotropy is, and then if anyone doesn't know, so it will be a quick introduction. So ergotropy is this quantity, this epsilon, which as you see is the maximal amount of work that you can extract from a system by doing unitaries. So this is the initial energy, right? So this is the initial state. H is the Hamiltonian, right? So the initial energy minus the final energy minimized over all the unitary evolutions that you could do on your raw. Right? And then, importantly, the final and initial Hamiltonians are kind of assumed to be the same, which means that, you know, by the end of the process, your battery returns to be the battery, right? So you kind of do not mess with the structural integrity of the system while extracting some energy from it. Right, and then there is this very convenient way of writing this minimization. It can be done in kind of final form, right? So the final state that sort of delivers this minimum is called a passive state, and it's just a state with reordered eigenvalues of rho in the eigenbasis of the Hamiltonian. So it looks like in a simple way like this, right? So this E's are the energy levels, and then what you do with this unitary rotations is that you put the largest eigenvalue on the ground state, and then the next to the largest one to the next level, et cetera, right? So this is the standard picture of ergotropy, right? And it has already been kind of for quite some time been used as a standard measure of charge in a quantum battery, right? Or charge level, right? I mean, the word charge is basically charged with many meanings. So in this case, when every time I say charge, I don't mean like an electric charge or anything, but just the amount of useful energy in the battery. Right, so it's again, I mean, it's typically measured by ergotropy, and we can immediately see a potential problem of using this measure, right, in any realistic scenario. Because let's imagine this very simple picture where the device is not a phone, it's just a weight that you want to lift, right? So it's a very simple scenario where your system essentially goes from state rho to rho passive, right? And then while doing that, essentially it loses epsilon amount of energy, right? And ideally, you would like this epsilon amount of energy to appear in the weight, right? So you basically did this process, right? It lost its charge, and you want this charge to see used for something good, right? Now, but the thing is that this process, right? This epsilon is defined for unitary evolutions, right? But every time you do something like this, the evolution both on the system and the battery is going to be open evolution, right? So it's not going to be unitary dynamics. So there is no guarantee that you will, first of all, lose epsilon here and you will gain epsilon here. So in and of itself, this is not a trivial problem. And of course, studying this kind of ergotropy transport situation, right, as a, again, proxy for powering a device is useful also for the fundamental sort of understanding whether ergotropy is, first of all, a good measure of charge in a quantum battery. Right, so let me be a bit more specific what I understand by ergotropy transport, right? So imagine that you have your battery, right, and then you have your whatever device, right? It's just these are just two systems. Like, of course, I will at some point talk about 2 qubits, so it can be very simple, right? And then you do some a global evolution on B and D, which in this case is going to be unitary. Of course, like future work should explore more general channels, but let at this point assume that it's a unitary channel. Right, and then you end up with a final state, which is denoted by this tilde, right? So rho BD goes through some rho BD tilde, and of course we can ask what the ergotropy of B is at the end and what the ergotropy of D is at the end, right? So basically, just compare ergotropies at the beginning and at the end, right? Now, we want this transport unitary to be energy conserving. Again, if the battery is powering your device somehow autonomously, right? So it's like a phone in your pocket, right? I mean, you don't want any energetic intervention whatsoever, which means that indeed your unitary must conserve energy. So this UBD should commute with HBD, which is the Hamiltonian of B and D, right? And in this case, we assume that the direct interaction between the two is sort of negligible, right? So we have HB plus essentially HD, right? So non-interacting systems and a unitary that sort of commutes with the Hamiltonians. And again, I mean, just to again study the transport problem, we just look at the ergotropy gain, which is a positive way to look at it. We could of course look at ergotropy loss, right? Because this is typically what you expect, something lossy happening, but we sort of concentrate on the positive. So we look at the gain, which is basically the final ergotropies, local ergotropies minus the initial local ergotropies, right? And of course this is just by rearranging the terms means that this is ergotropy received by the device minus the ergotropy lost by the battery, right? So this is kind of exactly the kind of loss or gain situation that we want to sort of address, right? So this is the main objective quantity that we're going to basically look at, and the energy conserving unitaries are going to be the processes that we do, right? So if you kind of remember anything from the talk, I mean, at least let it be that these are the main quantities, right? I mean, the results are, as always, kind of, they change or develop or anything. Now, again, so we have our process, and what we, first of all, do, right, we rewrite this ergotropy gain as a change in the ergotropic gap in BD, in the total system. Now, ergotropic gap has been introduced in this paper by Mukherjee et al. In 2016, and it's just the difference between the global ergotropy of the total system minus the sum of the local ergotropies. It is called ergotropic gap, and it's always non-negative. And yes, and the gain is essentially the difference between initial ergotropic gap and final ergotropic gap. Okay, so, and of course, from this quantity we see, since these both are non-negative quantities, we see that the ergotropy gain will be non-positive, so we will always have loss whenever the initial state has no ergotropic gap, right? So if essentially, this is lesson number one, right? So an energy conserving unitary cannot generate ergotropy out of nowhere, which sort of makes sense. Although of course it's not trivial by itself to prove such a thing, right? Because these are local optimizations versus global optimizations, but intuitively it makes a lot of sense. Okay, so and since the ergotropic gap has already been connected to correlations between the constituents, right? I mean, there is like a body of work that, and I'm not citing everything. No, this was some of the main thing that I had on top of my head, right? So those are some papers that already indicate some connection between the gap and correlations, which already sort of suggests that there should be some connection between ergotropy gain and correlations in the system, right? So this is already something to keep in mind. And then, yes, let me start with 2 qubits, right? So the simplest thing that you could imagine in this situation is you have 2 qubits. So imaginably, the battery is charged, so you have more population on the excited state and less population on the ground, and in your battery sort of meets the energy, so it doesn't have any ergotropy. And keep in mind that this very classical picture where you just have levels and populations is just a picture, right? I mean, so we generally consider general quantum states, right? So we don't need, we don't make any classicality assumptions or anything like that. Yeah, so the result number one is that, whenever, the initial state of B and D is not correlated, right? So if it's just a product state, then the ergotropic gain is going to be non-positive, so we will always have some loss in the system, right? And the other thing that we find is that, for most correlated states, the ergotropy gain will be positive, right? So presence of correlations doesn't mean that ergotropy gain is necessarily going to be positive, right? So it's not a one-to-one correspondence, but for most of them, it is going to be positive. Right, but since two qubits are kind of a boring system to study anything physical, right? So let's just look at relatively relatively more practical use one could make of just two qubits, right? So let's consider an ergotropy wire. Namely, let's imagine that these are like some kind of this is some kind of a contact between a larger systems exchanging work, right? And then we just use these 2 qubits because they are the wire, right? So in a very idealistic situation, so ideal channel product state, right? We would start the wire completely empty in a sense that, both qubits are in the ground state, right? So nothing is happening. Then we do a sigma x, we just do a bit flip, and then we just, inject ergotropy E into system 1, right? Into the battery, let's say. Right, so then we do a swap operation between basically B and D, right? And then we basically take this ergotropy from B and then we transfer it to D, right? Something very, very simple and trivial. And then we essentially do another bit flip, a sigma x operation on the device, or well, on the end side of the wire, right? And then we basically extract the ergotropy that we injected, at the beginning of the wire, and then we just get it at the end, and then the cycle is closed, and then we can basically repeat this infinitely many times. But this is a very idealistic situation, right? So what happens if the channel is non-ideal, right? So imagine your unitary is some swap plus epsilon, right? Because of course you can never do anything ideally. So there is going to be, there is going to be always, some noise in the system, right? And in that case, the first part of the, of the operation can be done as before, but then this epsilon is going to introduce some impurities into the, into the qubits, and then you will do your sigma x, and then you will extract some ergotropy that is a bit smaller, right? And then you will essentially close the cycle, but not close it properly, so you will already start with some noise, and then once you repeat this again and again, things are going to deteriorate and deteriorate. Right, so yes, so the transport will become lossy. So now let's consider the same situation where we sort of tolerate some noise in the channel, right? But now we start with a correlated state, right? Because we sort of understood that there is some hidden ergotropy, right? Some ergotropy hidden in correlations that we could use locally, right? And yeah, so imagine we start with an entangled state, which is like this, right? So it's when this kappa is small, then you are basically at 0 times 0, right, approximately, plus something, you know, on the excited states, right? Then you do exactly the same thing. So you do a bit flip, right? So you charge your start of the wire, right? You do the channel, you transfer something, and then you extract a little bit, and then what you find is that, you know, the extracted ergotropy is going to be E plus something of the order of K, kappa minus something of the order of epsilon, and this thing can be positive. Right, so you can have a gainful transport, and yes, so and this gainfulness is going to go on for kappa over epsilon iterations, right? So you will have a number of iterations, of course, if this number is larger than 1, which are gainful, right? And then you know, you will have you will transfer a total amount of ergotropy through this wire that is going to be of the order of you know, E times kappa divided by E, right? So this is a fairly simple kind of counting. And you know, like in a very like simplistic case, just to throw in some numbers, right? I mean, you can imagine that this kappa to be pi over 8, this epsilon could be some 0.01, you know, with whatever, you know, additional term. I'm not going to bore you with details, right? And then you can basically show that, you know, you calculate and you see that the initial ergotropic gap, which was the resource for your losslessness, right, can be like very small, like 0.3 E. Yet you can transport like 11 E amount of ergotropy through this wire, right? So basically it is a perfect lubricant for this for ergotropy transport, right? You add a little bit of correlations, and then you can all of a sudden transport like a huge amount of ergotropy without any losses. Okay, so this is a kind of the one case of use. Yeah, so I'll wrap up like in 1 or 2 minutes, right? Okay, so in larger systems, the situation is a bit different, right? So the general idea is again the same. So it's the ergotropy gain is given by the difference between the ergotropic gaps. It's just ergotropic gap can be positive, you know, even for product states, right? So when you have larger systems, you know, there is this notion of you know, activization, right? When you just compose 2 passive states, and then you get an active state without anything. They just don't know about each other, but the global thing is active, right? So it's been known for a long while, which means that, you know, you don't need basically correlations to achieve what you want. But however, correlations do matter. So, you know, if you randomly sample states and unitaries, right? So this looks a bit complicated, but you know, hopefully I will walk you through very quickly. So, you know, you can consider different configurations, right? You have 2 qubits. And then you see that if you sample product states, you know, the ergotropy gain is never positive, right? So it's cut exactly at 0. So everything is negative, right? When you have a bit larger system, like 2 times 3, then you have some positive ergotropy for product states, but most of it, the bulk is still in the negative, right? And if you go to larger systems, then basically the product states are going to be extremely useless with regard to ergotropy transport. Although you will have some positive values somewhere here, but you know, they will not matter, right? And then you can do the same sampling, but for separable and general states, including your entangled states. And then you see, of course, that, you know, entanglement is very useful, right? Because if you have like general states, then you have good chance of having positive ergotropy, especially as you go to higher dimensions. Right? Then you can basically sample this with respect to, you know, change in the mutual information to kind of make this connection between ergotropy and information kind of quantitative. So you have some informational quantity and you have your ergotropy, and then you get this almost linear connection. So to gain ergotropy, you have to lose some mutual information. So this is also, I guess, an important insight into the role of correlations in this game. And then, yeah, what you see is that, you know, for larger systems, you essentially get some concentration of measure, right? So things become very thin, right? So although for entropy, you know, concentration has been known for a while, but for ergotropy, it was not known. So this was the first time that we noticed it, and then we sort of showed that you can actually prove it analytically, but of course I'm not going to go into details. So this is a summary that I will, I guess, not articulate, right, and then developments.
Go ahead.
Yeah. Hmm?
Go ahead.
All right. Okay. So, so the summary is yeah. In the end of the day, yeah. So transporting a given amount of ergotropy is easier if the systems are correlated, right? So this is something that we establish, right? So correlations are of course not necessary or sufficient, right? But we do see that if we are talking in terms of generic sort of properties, if you have correlated states, then yeah, you will generically have like more ergotropy transport, although again it was not necessary. Right, and then yeah, basically we are able to also show that ergotropy as a mathematical function of state is Lipschitz continuous, and for many body systems it is going to basically concentrate. So that's why you would see like some very sharp kind of relationship between information and ergotropy in these kind of graphs, seeing that things become very deterministic. Yeah. So thank you for your attention. And, yeah.
Okay, any questions?
Thank you, Karan, for the talk. I have a quick question. Are there any trade-offs between extracted information, between transmitted information and ergotropy, or any constraints?
I mean, at this point, I would say it's not a trade-off. It is rather basically a positive relationship. So I mean, the more information you can transmit, the more ergotropy in the end of the day you can transmit also. But we didn't like specifically look at that like in more rigorous ways. So maybe there are some kind of negative relationship bridges. I will not know. But like again, on average, it's a positive relationship.
Okay, thank you.
Any other question? Oh, yeah.
Thanks for the talk. So in the ergotropy wire, you show that if you have the correlation in your states, and then you can actually have the thing for like transports. So I wonder, like, in the end of this cycle, like, how the correlation changes after you do this amplification. Can you just keep doing this cycle and keep use and reuse this correlation?
Thanks for the question. This is a very good question, and indeed, basically, the main resource of this lossless transport, right, is this ergotropic gap, right, and it is sort of directly connected to correlation. So basically, you use up this resource, and in parallel, you use up correlations. And once they are done, you basically become lossy again. So it's, yeah, it gets used up.
So I have a related question. How much ergotropy you need to create such correlations? I mean, because it looks magic that you got something out of.
Yeah. So I mean, if you look at this quantity, right, so this is the amount of basically energy or work that you need to expend to create the state. So it's like in this case, like in this example, it's 0.3 E. Right, but yeah, it allows for more. But I mean, you use it up, like slice by slice. No, it's basically you, little by little. Yeah.
Okay, Fede, go ahead.
Is ergotropy an experimentally accessible quantity?
Well, I mean, if you actually think in terms of qubits and sigma access, very much so. Yeah, I mean, you can do it in NV centers. You can do it in NMR settings. I mean, in NMR, it's basically how you detect a signal, right?
But should I optimize over the set of unitaries, or is there a easier recipe?
Well, I mean, yeah. I mean, so I mean, the problem with ergotropy is that you need to know the state, right, to basically optimize the unitary.
Okay, so sorry, I rephrase. So if we want to use ergotropy as, for example, a witness of entanglement of quantum correlations, so you don't know the state, can you?
I mean, in some limited situations, when you know something about the state, then you could basically engineer these kind of things. But in general, of course not. I mean, if you know the state, you will already calculate the correlations, right? So I mean, all these witness conversations are mostly basically people point to connection between the two quantities, but it's not a real witness as far as we know. I think.
Any other question? If not, let's thank the speaker again and all the speakers of this session. Okay, then we'll see each other tomorrow. Or not. Wait.
Sorry, I just remembered that yesterday I found a ball and a hat at the restaurant. None of you here left them, right? If you know who they belong to, otherwise.